Hello, this is Professor Keen. Today I want to talk about Chapter 4 in A Student's Guide to the Great Physics Texts. This chapter is titled Mueschenbroek's Wonderful Bottle, and the reference is Franklin's Experiments and Observations in Electricity, which was published in 1769. This is reproduced in Chapter 4 of A Student's Guide to the Great Physics Texts, Volume 3. You might remember in our previous lecture, we were talking about Franklin's letter number 2, which was dated 1747, and in this letter, Franklin introduced the terminology of positive and negative electricity. According to Franklin, every object possesses a kind of stock of electrical fire. So you might imagine it this way. So, according to Franklin, all objects contain a stock of what he calls electrical fire within them. So if you had two objects, maybe we'll call them A and B. I'll draw them right here. Here's object A and object B. They would, just by virtue of being material objects, contain some equilibrium level of this electrical fire. So you might imagine it goes up to here. Of course, this is an invisible fluid, but we're trying to represent it by some level like that, right? And what happens is when they are rubbed together, the objects can go out of equilibrium. Go out of equilibrium. So I'm going to redraw them, the same objects. And whereas the equilibrium level was here, maybe after rubbing them, this one has acquired some of the electrical fire from object B, so it has too much electrical fire within it, and the other object has lost some of its electrical fire. Okay, so according to Franklin, object A would then be, he would say, positively charged, and object B would be negatively charged. This is Franklin's terminology. Okay, here's object A and B. Okay, he would say they become electrified, and how much they become electrified, of course, depends on the kind of material and perhaps other factors. Certain objects tend to acquire this electrification, certain other objects tend to lose it. Okay, so as an example, when you rub glass with silk, if object A is glass and object B is silk, the glass tends to acquire the electrification from the silk, so it would become positively charged. On the other hand, certain other substances like plastics or PVC or resins, they tend to lose electrical fire when they're rubbed with, for example, fur. So object A would be the fur and object B would be then the PVC or the resin. So the resin, when you rub it with fur, or the PVC pipe, when you rub it with fur, would become negatively charged. Okay, so these objects, according to Franklin, will remain out of equilibrium until somehow the electrical fire is provided a path to re-equilibrate. So the objects remain out of equilibrium until a path of some sort is provided for re-equilibration. So they're out of equilibrium until then. So they would need to be conducted, we would say, by a conducting material. They need to be connected by a conducting material. They would need to be connected by a conducting material. Like if you took these two objects, glass and silk, rub them, they're out of equilibrium. So long as they're not touching each other, they will remain out of equilibrium. But if you touch them, they will reacquire equilibrium. Or if you put a copper wire between them, okay? If you have these resting on wax or some other insulating material, or other insulating material, they would just remain electrified. That is why often Franklin will put these on a table that's covered with wax. That would be insulating. That way, whatever electrification you give them, they will tend to keep that. By the way, we should probably talk about classifications of materials into insulators and conductors. So why don't I make a table right over here? And we'll talk about classifications of materials. This is going to become useful when understanding what Franklin talks about and in our subsequent work in this class. We tend to classify things into conductors and insulators. By the way, this is not the terminology that Franklin uses. He uses conductors. You'll see why he calls them this in a moment. He calls conductors non-electrics. You'll just have to get used to his terminology when you're reading his paper. And he calls insulators electrics per se. Okay, why does he do this? An insulator, he calls it electric per se. Per se means sort of according to itself or by itself or innately. And it's because when you rub an insulator, like glass, it will become electrified. It doesn't immediately discharge through the rod. It kind of holds on to this charge because the charge can't move through it to discharge. So he calls that an electric per se. And he calls conductors non-electrics. This, again, might sound a little bit counterintuitive, but if you try to charge up a conductor, the charge will quickly disperse throughout it, and if it's touching the ground, it will all discharge through the ground. So they can't sort of hold on to a charge as long as they're touching the ground. So he calls them non-electrics. Anyhow, I'll probably use the term conductors and insulators because those are contemporary terms. What are some examples of conductors? Well, most metals, like gold or silver or aluminum, would be conductors. Copper, these are all conducting materials. Also, if you have water that is ionized water, which most water has some ions in it, hydrogen and oxygen ions from dissociation of the water molecules, but they'll especially be ionized if you have salt in it, because the salt will break apart into sodium and chloride ions, and so those can conduct electricity. So ionized water, and for that matter, ionized air, like plasmas also. So if you have lots of positive and negative charges in the air that are freely floating around, it's ionized, then it's a good conductor. On the other hand, insulators would be things like wax or plastics, resins, plastics like PVC, things like that. Glass is an insulator. Amber is an insulator. Gemstones are insulators. He uses dry wood as an insulator. If you have deionized water, so if you take all of the ions, the conducting charges out of the water, it will be deionized, and that will be a good insulator. And by the way, these are general classifications, but certain things are better conductors, certain things are worse conductors, certain things are better insulators, certain things are worse insulators. So there's a continuum here, but we tend to classify things like this. Okay, and maybe for the sake of completeness, I should also mention at this point semiconductors, which play a very important role in modern technology. Semiconductors are materials that are insulating under some conditions and conducting under other conditions. So group 14 elements in the periodic table, like silicon, is a very important semiconductor, and germanium is another important semiconductor. These tend to be insulating at low temperature, and as you heat them up, they become conducting. So there's some transition where they go from insulating to conducting. Those are called, by the way, intrinsic semiconductors, as opposed to extrinsic, where you can make them conducting or insulating by doping them or adding other kinds of elements. But that goes far beyond what we want to talk about here. So let's just leave this classification as it is.